Hi everyone, this is Michał again, and today we'll go through the most recent questions from performance which have been seen in the actual EASA exams across all authorities in the past 30 days. So without any further ado, let's jump in and tune in into those 7 questions. For the first one, during a constant descent arrival, a higher than forecast headwind is experienced, putting the aircraft below the profile. What action is to be taken by the captain? So of course, if your headwind increases, then your gradient through the air will also increase because your ground speed is decreased, meaning you'll find yourself below the profile that you actually wanted to fly or that you initially planned to fly. In that case, if you're flying a constant descent arrival, meaning you're calculating a specific rate of descent in order not to have a step down fix, so in order to continuously descend instead of descending and leveling off, descending and leveling off, in that case, you'll just reduce the rate of descent to regain the profile and then go back onto your desired path. And there is nothing wrong about this as long as you're not busting the hard altitudes at specific waypoints. There is nothing unsafe and there is nothing wrong regulation-wise with going slightly faster or slower than you wanted, as long as you catch up and you are at the desired altitude, at the desired fix. And you'll see this happening during approaches as well very often, especially non-precision approaches. So where you have to fly a continuous descent final without vertical guidance, you will need to calculate the rate of descent based on your ground speed continuously during the procedure. In that case, you'll have on the plate something called contracts, meaning your distance and altitude cross-check table. So you'll see that at 5 DME, you need to be at, for example, 2,500 feet. And if you find yourself lower or higher than that altitude, there is absolutely nothing wrong about simply catching up, so reducing or increasing the rate of descent, as long as you are above 1,000 feet. So we are keeping in mind the stable approach criteria. And even then, if you find yourself up to 100 plus minus of these contracts, then there is nothing wrong about simply correcting to regain back the path. Any more than that, regulations require us to go around as the approach becomes unstable. However, in that case, you absolutely simply reduce the rate, you regain the profile and continue with your arrival and then of course your approach. So now for question number 2. At the destination aerodrome, the landing distance available is 3,000 meters. The appropriate weather forecast indicates that the runway at the estimated time of arrival will be wet. For a commercial flight, the mass of a turbojet airplane at landing must be such that the airplane can be landed within. So this is one of the most classic questions and you'll find a lot of iterations of it. So either a commercial turbojet or a commercial piston aircraft, wet or a slope. And here I must say that all the factors that you need to calculate and need to use for the calculations can be found in the performance cap. So if you can use it for the exams, then of course always cross-check it with this, as all the numbers will be there. In case of a commercial turbojet aircraft, the regulations require us to make sure that we can land within the 60% of the given distance. So all you need to do here is to apply the 60% factor to the 3,000 meters. And then because the runway is wet, we need to add an extra safety factor of 15%. And this 15% factor always needs to be added on top if the runway is wet. If the runway was dry, then we would simply skip this step and have the answer right away. However, if you calculate 60% of 3,000 and then divide it further by 1.15, meaning the 15%, the answer you should get is 1,565 meters, and this should be correct for the commercial operations of a turbojet. If it was a piston aircraft, then the factor required is 70% of the distance available. So instead of getting 60 of 3,000, you would calculate 70% of 3,000. And here also remember that this is only for commercial flights. If you're flying private or general aviation, then these factors are not needed to be taken into account. And here also remember that aside of runways being wet, there are different factors for grass, paved, down and up sloped runways. So keep that in mind, and all of these numbers can be found in your cap. Question number 3. During a cold day with high atmospheric pressure, a multi-engine piston pilot is climbing at a speed for minimum controllability, so VMC. When it suffers an engine failure, the pilot should expect. So if the day is cold and the atmospheric pressure is high, then one thing that you need to remember is that your engines will produce more thrust than in the opposite um, situation and the opposite environment. So if their day is hot and low pressure, then your engine's producing less thrust than in the situation given here in the question. So if we are producing more thrust, that means that in case our engine dies in a multi-engine aircraft, the other engine, so the engine that's alive, will produce more thrust, meaning more moment, meaning uh, reduced controllability. And this is what the authors of the questions are trying to get us into. And here also remember that our VMC and VMCA, the only difference is that the VMC is a speed that we need to think about during the initial climb. So this is when we have a maximum thrust for our aircraft as we are just after the takeoff, meaning when our engine is producing a lot of thrust because the day is cold with high atmospheric pressure. This means that if an engine dies, we will have reduced controllability because our VMCA will be high because we'll need to more authority on our vertical stabilizer in order to keep a straight and level flight. Now question number 4. So when compared to still air conditions, a constant headwind component, so what does it do? And there are a lot of questions in performance asking us about headwind and tailwind components. And the key thing here to remember is that headwind and tailwind will change our maximum distance that we can cover in an aircraft. However, they do not affect our endurance at all. So the time spent in the aircraft will always be the same because no matter how much distance we travel, no matter what our ground speed is, our engines will work for the same amount of time, no matter the wind. So knowing this, of course, we can immediately take the first answer out of the question, increase the angle of flight path during the climb. And this might be true. And the reason it's true is because the flight path angle is the angle that we're actually flying through, and any headwind or tailwind component will actually make the flight path through the air steeper or shallower, depending if we have tailwind or headwind. The best rate of climb is always through the air, meaning no matter if we have tail or headwind component, it will always be the same. We might reach the desired height in a shorter or longer distance. However, the time to reach it, so the rate of climb will always be the same. And similarly, the angle of climb will also always be the same. The only thing that will change will be the distance that we cover. However, through the air, the distance and the angle of climb will be the same. The only thing that changes is the flight path, so the so-called vector or the bird that we see. And this is the one that essentially follows where the aircraft is actually going. And this will be affected by headwinds and tailwinds. And remember that the bird, so the flight path vector, is reliant, it's also called the speed vector, is reliant on the speed. And if you're flying straight and level on your PFD, you'll see the bird exactly on the horizon, even though the nose of your aircraft, so the longitudinal axis, will be slightly tilted up in order to create some angle of attack. For question number 5, during a descent with constant Mach number below the Tropopause and EASA conditions, how do the TAS and CAS change? So if you remember the eat chicken tikka masala mnemonic, so you have 3 fingers, chicken tikka masala, calibrated, true, and Mach. If you are descending with constant Mach number, this means that both CAS and TAS will increase, which of course makes sense because as you go lower, the air is denser, so your CAS will start increasing, as well as the temperature will start to rise. And of course, your Mach number is a ratio between TAS and local speed of sound, where local speed of sound is dependent on the temperature only. You can calculate it roughly with a formula of 39 times the square root of temperature in Kelvin. And so in this case, both will increase. However, just something to mention is that the examiner here is saying below the tropopause, and this is a very important consideration because if you're flying in a tropopause, then TAS and Mach will not neither decrease or increase. They will stay at the fixed same value because the temperature in tropopause does not change. So this is something to remember, as this can trick you, especially for this type of exams, and CAS will continue to either drop or increase just as is woozed below the Tropopause. So for question number 6, how does runway slope affect allowable takeoff mass, assuming other factors remain constant and not limiting? So this is something that can also be cross-checked with some of the graphs in our mass and balance performance caps. However, the key consideration here is, okay, we know that we're flying or taking off with a uphill or downhill slope, and the big question is now whether it will be easier to accelerate or more difficult to stop. So if you're flying on a downhill runway, then of course it will help you with acceleration. However, it will prevent you from stopping. So now the question is, which one is more affecting? And in this case, actually, a downhill slope will increase your allowable takeoff mass. So a downhill slope, so the extra acceleration, the boost given by the downhill slope will be much bigger than the problems with stopping, as both will be increasing in different directions. However, the acceleration is much more important in this case, and this means that it will increase your allowable takeoff mass because it will be much easier for you to accelerate and go with your flight. And the last question in this case. So the combination of factors that most require a low angled flap setting for takeoff is so this is also an interesting question, and as you can see here, it has all 60 comments, which is quite a lot. So it stirred a lot of discussion. So what I'll say here before we go a bit more in depth is that if you see low angled flaps, meaning this will mean that you will take off much later. However, you'll have a greatly increased gradient of climb. So if your takeoff distance increases, you will never want to take off in a short runway ever. So if you have a low angled flap, especially for the answers and questions for the ATPL exams, if you see short runway and low flaps, never choose that answer. And this makes choosing this answer very easy just based on this one factor, because all three have short runways instead of this one. However, it all makes sense generally because when you have distant obstacles in the climb out path, that means that you are concerned with things that are further away from the airport. So you want to climb to a high altitude quicker rather than close by obstacles. And flaps always decrease your climb gradient because they increase not only lift but also some of the drag. So if you have distant obstacles, then you want to climb out faster to achieve a higher altitude later on, and this will be done by selecting lower flap settings than usually. And these lower flap settings will also help you fly with a faster airspeed, meaning in high elevation airfields with high ambient temperatures, it will just be much more easier to take off safely if there are no obstacles close to the runway. So this will be the correct answer. So always remember for the questions that the low flaps, long runway, this will help you answer most of the questions. So thank you for joining in. I hope to see you in the next video, and I wish you all the best as always. Bye-bye.